Hey, chemistry, here is our Unit 2 Common Assessment Review. In Unit 2, we really only learned four things: physical and chemical properties and changes, how to calculate density, the trends of the periodic table, and how to draw Lewis dot structures. Let's get into it. Physical and chemical properties are ways that we describe how an object is and how it changes. So physical properties you can observe with your senses. That's things you can see, you can touch, you can taste, you can smell. However, chemical properties indicates how a substance will react with something else. The big difference is a physical property can be determined without destroying something, whereas chemical properties will be changed into a new substance after a reaction. For example, some of the different other ways that we describe this is what are called extensive and intensive properties. Extensive are physical properties that can be altered without changing the substance's identity. So for example, volume is an example where I can measure the volume of this calculator, and I don't have to destroy it in order to do that. I would just get a ruler and check it out. I can tell you about the shape. I can tell you about its mass. I can tell you the temperature. If I had a thermometer, I could tell you the length. But some intensive properties determine on what this do not depend on how much of a substance is present. So for example, density, if I had a piece of paper, the density would be the same whether I had a teeny tiny slip of paper or the whole thing. Melting point, boiling point. That's a good example is ice will always melt. Whether you have a giant block of ice or a small block of ice, it will always melt at the same temperature. Boiling is the same, etc. So as you're trying to figure these out, ask yourselves, is the matter being destroyed? Is it turning into something new? If it's turning into something new, that's a chemical property. Or if it's just physically being altered, that would be a physical property. So one of the CERs we did when we went over this was baking soda and vinegar mixed together and form a bubbling gas. So the claim would be that this is an example of chemical change. And some of the evidence would be that the baking soda is a solid and the vinegar is a liquid. And yet when they react, it turns into something new, a new form of gas. Now you need to be careful. Just because it goes from a solid or a liquid to a gas doesn't mean that it's chemical. It's because you're literally forming something new. But if I were to boil water and turn it into a gas, that is not a chemical change because it's still water. I mean, it's steam, but it's still water. Baking soda and vinegar are no longer baking soda and vinegar when they mix. They produce a gas. I believe it's carbon dioxide. Okay. After that, we learned density. Density has a very simple equation. Density is mass divided by volume. The trick that you can remember it is density breaks your heart. If you look at it, it's an M over a V. And it tells us how many particles there are in a certain space or volume. And we are going to measure these with the units of grams or kilograms for mass, and then milliliters, centimeters cubed, or meters cubed for volume. The calculations are fairly simple. Set up your equation, D equals M over V. Annotate your problem. So I have volume here and mass here. I'm looking for density. Plug it in, and then divide and solve. Your units are just going to be your top unit divided by your bottom unit. So you'll need to look in your problem. So I have grams divided by centimeters cubed, just like if I were to put the numbers or the units on the numbers in the calculation. Okay. You will occasionally have to solve for the volume. If you get stuck on doing that, reach out to me or Mr. Barone and we can help you out with that. Next, we learned what were called the periodic trends. So as you moved across or down the periodic table, what were some of the things that we noticed? And so the first thing that we talked about was atomic radius. This is the size of the atom or the size of the atom or element. And what we learned is that as you go across the periodic table to the right, and as you go down the periodic table, we could observe a couple trends. Let's look at this graph to see it. So as we go across, we see that the size seems to go down. Then we go down the periodic table and the size seems to go up. then we go back to the right, it goes down, we go down the periodic table, and then across, and the size seems to go down. So what we see is that as we go across the periodic table, we see that the size or the radius decreases. And we see that as you go down the periodic table, the size or radius increases. Okay, and our reason for that was as you go across the periodic table, you're adding in more protons into the nucleus, and those protons are going to pull the electrons in a little bit closer, which means that that effective radius is getting smaller as you go across, as more protons pull in. However, as you go down, you're adding a new whole orbital or a new whole energy level. So that means that the overall atom is getting smaller or getting larger as you go down the periodic table. So as you go across, more protons pulls in. As you go down, you get more energy levels, so those electrons are further out. Next, we talked about what was called the first ionization energy. This was the energy required to rip away an electron. So if you have a really high ionization energy, that means you want to keep your electrons. Okay, so high ionization energy means you're going to keep your electrons. We can see that as we go across the periodic table, so from 1 to 2, the ionization energy goes up, and then there seems to be a big decrease as we go down the periodic table. Then it goes up again, big decrease, then it goes up again. So what we see is as we go across, we see the ionization energy increases. So another way to think of that is that the elements on the right side hold on tightly to their electrons, while the elements on the left side are more willing to give them away. And then as we go down that periodic table, you can see that the ionization energy is decreasing. So ionization energy decreases. And these two things are linked. Remember, we said the size decreases as you go across because there's more protons, and the protons pull the electrons in tightly. If they're pulling those electrons in tightly, it's going to be really hard to rip them away, so they have really high ionization energies. So those two things are linked with each other. They're not just random. And in fact, they're even linked to the third thing we learned, which was called electronegativity. And electronegativity is the willingness to steal another electron. Willingness to steal another electron. Okay, so again, as we go across the periodic table from 1 to 2, I think this graph is off by 1, but we see as we go across the periodic table from 3, we see this increase, and then as we go down, the electronegativity decreases, and then it increases as you go across. So again, as we go across, the electronegativity increases, which means that it's more likely to steal an electron. So elements over here in group 6A, 7A, they not only want to hold on to the electrons that they have, they want to steal an electron from somebody else. Whereas the elements over in groups 1A and 2A, or 1 and 2, they're not only willing to give away their electrons, they don't need to get any more. They're content with what they have. Same thing is true as we go down. We see that electronegativity decreases. And you can think of that as because they have so many electrons, they don't need to get another one. It's a very simplified way to describe it, but it's a good way to remember it. So we see that the electronegativity decreases. You may want to watch this section of the video 2 or 3 times to really figure it out. I am going a little quickly here, but just make sure that you know that those 3 trends exist. And the last thing we did is we learned Lewis dot structures. Remember, this is where we focus on the valence electrons, and then we write the charges if it's an ionic compound, and we write the bonds if it's a molecular compound. So if it is an ionic compound, draw each element separately, move electrons from the metal to the nonmetal, and then write the charge in the top right corner. We will also show the nonmetal in brackets. So I'm going to put calcium in the center. Calcium is our nonmetal. We have chlorine. Chlorine has 7 valence electrons. You can look at the periodic table to confirm this. Calcium has 2 valence electrons. Chlorine, again, has 7. So what this means is calcium is willing to give its electrons away. So it is going to give 1 electron to this chlorine and the other electron to this chlorine. Now chlorine has 8 valence electrons. It's happy. Calcium also has 8 valence electrons, but remember, by giving those away, it acts like a noble gas on the level below. Because calcium gave away 2 electrons, it has a charge of 2 positive. Because it gave 2 negatives away, it becomes 2 positive. Each chlorine gained 1 negative, so they become 1 negative. And as a check that you can always use, add up your charges. 1 negative plus 1 negative, that's 2 negative, plus 2 positive, so the total charge is 0. And that's how you can always check your answers. So this is exactly what it should look like. The other way that we can do this is is for molecular compounds. In molecular compounds, remember, this is a nonmetal plus a nonmetal. So I'm going to put carbon in the middle here, chlorine all around it. Carbon has 4 valence electrons. 1, 2, 3, 4. Each chlorine has 7. These are both nonmetals, which you can confirm in your periodic table. And what I see is that I can form bonds between all of my chlorines and my carbon. And if I do that, we just need to confirm that each of them have 8 valence electrons. Each line represents 2. So each chlorine has 2, 4, 6, and then this line counts as 8. And that's true for all of my chlorines, whereas carbon here in the middle has 2, 4, 6, 8. The steps to solve them are here. So you can determine the total number of valence electrons, put one in the center, draw bonds, and then distribute your electrons accordingly. I think if you draw the electrons first and then kind of look at, okay, who's sharing, who's not sharing, that'll give you a pretty good intuition as well. But otherwise, this is a review of Unit 2. Hopefully it was helpful, and look forward to Unit 3 later this week.